Precipitation is when a chemical reaction occurs between two solutions and the reaction produces a product that is a solid. Let's look at an example of a precipitation reaction. Let's say we have a beaker with a solution of lead nitrate and we have another beaker containing a solution of potassium iodide. If we pour the potassium iodide solution into the beaker containing the lead nitrate, we observe a cloud of yellow solid appearing in the beaker. That yellow solid is our product, which is the precipitate of the reaction. We would say that the solid precipitates out when it falls to the bottom of the beaker. Let's write out the equation for this precipitation reaction. One beaker contains an aqueous solution of lead 2 nitrate, which has the chemical formula PbNO32. The other beaker contains an aqueous solution of potassium iodide, which has the chemical formula Ki. To predict the products of this reaction, we need to know what ions were in solution. We can find the ions using the technique of crossing over charges. Taking lead nitrate, we look at the subscripts in its chemical formula PbNO32. The subscript on lead is implied to be 1, while the subscript on nitrate is 2. We cross over these subscripts and say that our solution contains lead 2 plus cations and nitrate minus anions. We can write these out as Pb2 plus and NO3 minus. We can now do the same thing for potassium iodide. Since that has the formula Ki, we know that our solution has potassium 1 plus cations and iodide 1 minus anions. We can write these out as well, K plus and I minus. Now that we know the 4 ions in our solution, we can figure out the products of the reaction. To do this, we can take the cation from one reactant and combine it with the anion from the other reactant. Let's start with our potassium cations. These have a charge of +1, and so we can combine them with the anion from the other reactant, which is a nitrate ion. We cross over the absolute value of the charges to get KNO3, potassium nitrate, as our first product. Now we look at lead 2 plus. Lead 2 plus will combine with the remaining anion, which is the iodide ion. We cross over the absolute value of the charges to get our other product, which is PbI2, or lead 2 iodide. We can now write out our unbalanced chemical reaction. An aqueous solution of lead 2 nitrate plus an aqueous solution of potassium iodide yields potassium nitrate and lead 2 iodide. We use the aqueous subscript to indicate that we know both reactants dissolve into their component ions in solution. We know that both of our reactants are aqueous, but now we want to find out which of our products are aqueous. We can guess that at least one of the products is not aqueous since we observed a solid yellow precipitate. But we don't know whether the precipitate is potassium nitrate or lead iodide. Now we need to figure out which one of these formed our solid yellow precipitate. To do this, we need some more information, a chart called a Solubility Guidelines table. The first rule is that nitrate salts are soluble. In our case, one of our products was potassium nitrate, which has a nitrate ion and which is thus a nitrate salt. So we can guess that the potassium nitrate is soluble, and we can add an aqueous subscript to potassium nitrate. The second rule is that ionic salts containing alkali metal ions such as lithium 1 plus, sodium 1 plus, or potassium 1 plus are also soluble. In our case, potassium nitrate also contains potassium ion, further confirming that it is soluble in water. The third rule is that chloride, bromide, and iodide salts are soluble, although there are some exceptions. Salts of the ions silver 1 plus and lead 2 plus are 2 exceptions. In our case, we have an iodide salt, but it contains lead, which happens to be one of the exceptions to Rule 3. Lead iodide is therefore not soluble. We can now guess that lead iodide is our precipitate, and we can indicate this by putting an S for solid as a subscript in the chemical equation. Next, we need to balance our chemical reaction. We can see that we have two nitrate ions on the left side, and so we need the same number on the right side. So we put a 2 in front of potassium nitrate. But now we have two potassium ions on the right side, and so we need the same number on the left side. So we put a 2 in front of potassium iodide. We count and find that we have one lead ion and two iodide ions on both the right and left sides, and so our reaction is balanced. Now we want to take this chemical reaction equation and turn it into an overall ionic equation. This process consists of taking each aqueous compound in the equation and writing it out in terms of its constituent ions. When we write these out, we need to take care to keep the coefficients of each ion intact. Lead 2 plus ions plus 2 nitrate ions plus 2 potassium ions plus 2 iodide anions yields 2 potassium ions, 2 nitrate ions, and solid lead 2 iodide. Next, let's look at what's actually happening when the lead 2 plus ions combine with the iodide anions to form the solid precipitate of lead 2 iodide. The other two ions, potassium and nitrate, were there when the reaction started as ions in aqueous solution. They are also there in aqueous solution when the reaction is over, and so overall, they did not participate in the reaction themselves. They merely watched the reaction. So we call these spectator ions because they are present for the reaction, but they don't participate. So our spectator ions for this precipitation reaction are potassium and nitrate. We go to our overall ionic equation and cancel out the two potassium ions on the left with the two potassium ions on the right. We can also cancel the two nitrate ions on the right side with the two nitrate ions on the left side. This leaves us with our net ionic equation, which tells us the exact combination of ions that actually happened during our reaction. Notice how the net ionic equation is already balanced. Now let's look at this reaction slightly differently using particulate diagrams. We know from balancing charges and the balanced chemical equation that for every one lead 2 plus ion, we need to have two nitrate ions. So if we look at our starting solution in the particulate diagram, we have two lead 2 plus ions and four nitrate 1 minus ions. This makes sense because the ratio has to be 1 to 2. Looking at the particulate diagram for the starting solution of potassium iodide ions, we notice that we have equal numbers of potassium ions and iodide anions. This makes sense because the ratio has to be 1 to 1. We can then look at the particulate diagram after we mix our two beakers together to form our precipitate. In the precipitate that is forming, we see that there are 3 lead 2 plus cations in the diagram, as well as 6 iodide 1 minus anions. This ratio makes sense because of the 1 to 2 mole ratio between lead 2 plus and iodide. When our reaction is complete, we have lead 2 iodide in a 3-dimensional crystal structure. If we look at the remaining ions in our beaker, we see that we have 4 leftover potassium 1 plus ions as well as 4 nitrate 1 minus anions. These remaining ions are the spectator ions for our reaction. Let's consider one more example of a precipitation reaction. Suppose we mix a solution of barium chloride with a solution of potassium sulfate. Can we predict whether a precipitate will form? Our first step is always to write down the chemical formulas for our reactants and products. Barium chloride has a chemical formula of BaCl2, and potassium sulfate has a chemical formula of K2SO4. Since both of these are aqueous solutions, we can write them out in terms of their constituent ions. By crossing over the subscripts to find charges, we find that barium chloride becomes barium 2 plus cations and chloride 1 minus anions in solution, or Ba2 plus and Cl minus. Likewise, crossing over charges tells us that potassium sulfate becomes potassium plus cations and sulfate 2 minus anions in solution, or K plus, and SO4 2 minus. Now that we know what ions are in our solution, we can figure out the products of the reaction. We start with our barium 2 plus cations. Each barium 2 plus ion will combine with a single sulfate 2 minus anion, resulting in barium sulfate, which has the formula BaSO4. Next, we look at our potassium 1 plus cations. Because the chloride anions have a charge of -1, we can combine one potassium ion with one chloride ion to produce potassium chloride, which has the chemical formula KCl. We can now write down our unbalanced chemical reaction. An aqueous solution of potassium sulfate plus an aqueous solution of barium chloride yields barium sulfate and potassium chloride. Now it's time to figure out whether either product, barium sulfate or potassium chloride, produces a precipitate in solution. We once again need to use our solubility guidelines table. First, we can consider potassium chloride. This is a salt containing an alkali metal ion, potassium here, and so we know by Rule 2 that this compound is soluble. This makes the product potassium chloride aqueous and not a precipitate of the reaction. Next, we consider barium sulfate. On the solubility guidelines table, we can look at Rule 4. Rule 4 states that most sulfate salts are soluble, except specifically for the exception of barium sulfate. So we know that barium sulfate is insoluble, making it the precipitate for our reaction. In the chemical formula, we can add the subscript S to indicate that barium sulfate is a precipitate. Next, we can balance our equation. There are 2 potassiums and 2 chlorides on the left side, and so we need the same number to be on the right side. So we put a 2 as the coefficient of potassium chloride on the right side. If we count up the number of barium and sulfate ions, we can see that there is 1 of each on the left and 1 of each on the right, and so our equation is balanced. Now we want to identify the spectator ions. To do this, we need to break up our chemical reaction equation into an overall ionic equation by writing each aqueous reactant in terms of its constituent ions. When we write this out, we make sure to keep the coefficients intact. 1 barium cation plus 2 chloride 1 minus anions plus 2 potassium ions plus 1 sulfate 2 minus anions yields solid barium sulfate, 2 potassium ions, and 2 chloride 1 minus anions. We can see that potassium and chloride ions appear on both sides of this equation in equal numbers, and we can cancel them out. Therefore, they are our spectator ions. The net ionic equation then becomes sulfate 2 minus anions plus barium 2 plus cations yields solid barium sulfate. Notice that once again, our equation is already balanced. Alright, as a quick recap, precipitation reactions occur when 2 aqueous solutions are combined, causing a chemical reaction that produces a solid product. When determining how 2 aqueous solutions will react, the first step is to use the chemical formulas of the reactants to determine the different ions in solution and their charges. The easiest way to do this is by crossing over the subscripts of the chemical formulas to find charges. Next, combine the different ions in solution to produce 2 new ionic compounds, using the charges of the ions to determine the chemical formula of each product. Once the products are known, the solubility guidelines table can be used to determine which, if any, of the products is a solid precipitate. After finding the precipitate, the original chemical equation can be simplified by removing spectator ions, which are ions that stay dissolved and don't participate in the precipitation reaction. The resulting simplified reaction is the net ionic equation.